based on this definition, so you're gonna have this homogeneous system a minus lambda I times x is equal to 0. So we have to find out lambda and x that has a non-trivial solution in this case. So in this case, so it's going to be the solution of this one. It's going to be null space of the a minus lambda I. So this set in this case, this set is called eigenspace of a corresponding to lambda. Eigenspace consists of the zero vectors and all the eigenvectors of corresponding to lambda because this is subspace. Yeah, right. Then you can easily find the eigenvectors by using these equations. A minus lambda I times x is equal to 0. So we have to we discuss how to find out corresponding eigenvalues given eigenspace given eigenvalues like this, right? So the geometric view of the eigenspace was like that. So even though this matrix A can transform arbitrary vector x to the transformed space AX, the vectors in the eigenspace can be transformed to the eigenspace as well. And in eigenspace as well, you will have the same direction with a different magnitude, which is determined by eigenvalues lambda. Today, we will see a few more concept or the property of the eigenvectors eigenvalue. So first of all, eigenvalues of the triangular matrix are entries on each diagonal. So if you have an arbitrary scale matrix, to find the eigenvalues, you have to use some calculation to find out eigenvalues. But if your matrix is triangular, eigenvalues it's just its own main diagonal term. So let me give you an example. Here's the proof. For simplicity, consider the 3x3 case. If A is upper triangle, A minus lambda I has form like this is matrix A because this is upper triangular defined here, and this is lambda I was a 3x3 identity matrix. Then it's going to be A1 minus lambda A12, A13, A22 minus lambda A23, A33 minus lambda, right? So the scalar lambda is eigenvalues of matrix A if and only the equation A minus lambda I x has equals 0 has non-trivial solution. This is just the definition, right? That is if and only if equation has free variable, 그렇죠? Because this is homogeneous system. So if equation has free variable, right, it has a non-trivial solution. Because of the zero entries in A minus lambda I here, 그렇죠? We just say that this one, and this one is a pivot position candidate, right? So in other words, it is easy to see that this equation has a free variable if and only at least one of the entries on diagonal A minus lambda I 0. At least one of the entries of the diagonal of A minus lambda I is 0. If this one is equal to 0, or this one is equal to 0, or this one is equal to 0, then this matrix equation has free variable, so it has a non-trivial solution, right? This happens, right? Thus, this happens if and only if lambda equals to one of the entries of entries A1, A1, 2, A3 in A, matrix A. This is just the proof. So this is a theorem 1. Eigenvalues of triangle matrix, the entries on each main diagonal. This is the first theorem. The theorem 2 is like that. V1, V2, VR are the eigenvectors that correspond to distinct eigenvalues of lambda 1, lambda 2, lambda r of n by m matrix A. Then the set V1, V2, VR is linearly independent. So distinct eigenvalues, the eigenvectors corresponding to distinct eigenvalues are linearly independent. This is theorem 2. So first of all, so by the way, today and next week we will see so many kinds of proofs. So this is the pretty difficult, but please do not focus on the difficult part. Please focus on the theorem itself and please try to understand high level meaning. Please do not try to memorize all the proof. Okay. So this is just theorem 2. First of all, let's prove. Suppose that your eigenvectors v1, v2, vr is linearly dependent. 그렇죠? First of all, let's suppose your vector set linearly dependent. Since v1 is the non-zero, right? One of the vectors in the set is linear combination of the preceding vectors. 그렇죠? We already talked about this one in the previous lectures, right? If the set of the vectors are linearly dependent, one of the vector can be linear combination of the preceding vectors. 그렇죠? In this case, let P be the least index such that VP plus 1 is a linear combination of preceding linear independent vectors. 그렇죠? This one. 그렇죠? Then there exists color C1, C2, Cp such that C1 times V1 plus C2 times V2, Cp times Vp equals to Vp plus 1 because we just assume Vp plus 1 is a linear combination of the preceding vectors. Linear combinations. 그렇죠? So let's suppose that this is equation 4, right? And in this case, multiply both sides, left-hand side, right-hand side of the equation 4 by A. And using the fact that if we multiply A, left-hand side, right-hand side, it's going to be here and here, right? Then, by definition of the eigenvectors, which was AV equals to lambda V, this equation is going to be, looks like this. Lambda was scalar value, right? Let's say this is equation 5. Then multiplying both sides of 4 by lambda p plus 1 and subtracting result from the 5. 저 여기서 빼주면 multiplying lambda p plus 1 to 그렇죠? Here and subtracting from the 5, this one, then you're going to have C1 times lambda 1 minus lambda p plus 1 times V1. 그렇죠? blah 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 Cp times lambda p minus lambda p plus 1 Vp, which is equal to 0. 그렇죠? By definition, right? Let's say this is equation 6. So since V1, V2, Vp is linearly independent, 그렇죠? 여기 앞에까지는 다 linearly independent로 가정했으니까 linearly independent, the weight in equation 6, weight, this one, whole 0, because the V1, Vp are linearly independent, right? Right. But none of the factors lambda I minus lambda p plus 1, 그렇죠? This one, it's none of the factors lambda I minus lambda p plus 1 are 0, right? Because we just assume they are distinct, right? Because they are distinct. 그렇죠? 같지 않다고 가정했었죠? 그렇기 때문에 because the eigenvalues are distinct, right? 써 있네요. So here Ci, C1, C2, Cp should be 0 for all I is equal to 1, 2, 3, P. But then equation 4, 그렇죠? This one, this equation say that this one, if this one is 0, P plus 1 should be 0, but equation 4, P plus 1 it's not equal to 0 because it's not impossible because the this is eigenvector, so it should not be the 0 vector. So it's impossible. So this assumption is a fail, right? So in other words, this vector should be linearly independent. Okay? Linearly independent. This one should be linearly independent. That's it. In other words, distinct eigenvalues of the matrix A can have corresponding eigenvectors that are linearly independent. This is a theorem 2. This theorem 2 will be used in many many algorithm which is the diagonalization. We will talk about this one later. Anyway, this is just a theorem. Okay. Question. No. Okay. Then let's move to the chapter 5.2, the characteristication. Okay, so in chapter 5.1, we discussed what eigenvalues and eigenvectors are. In chapter 5.2, we will talk about how to find out eigenvalues. Then you can easily find an corresponding eigenvector, as you can see in the previous example, right? That's the characteristic equation. Okay, so to define characteristication, we have to go back to inverter matrix theorem. There were so many kinds of concepts, right, about invertible matrix, inverter matrix, where A was n by n matrix. Right? By using eigenvalue concept, we can extend further IMT, inverter matrix theorem. Here's two more things. First of all, the number 0 is not eigenvalues of matrix A. Then matrix A is invertible. Or if matrix A is invertible, number 0 is not an eigenvalue of matrix A. This is one more statement. We can easily compute. We can easily prove this one. Right. So by definition of the eigenvectors and eigenvalues, if lambda is equal to 0, then right hand side is going to be 0, right? Then because this is eigenvectors, AX equals 0 should have non-trivial solution. Then A is not invertible. Not invertible. Right? In other words, so in other words, if lambda is not equal to 0, A is invertible. So this is the new statement for the inverter matrix theorem. One more thing is that this is just definition. Determinant of the matrix A should not be 0. 그렇죠? Why? From the definition of the determinant. 그렇죠? determinant definition에서 얘가 0이 아니어야, 그렇죠? 얘가 뭐예요? 인버터블하다고 정의가 있었으니까 그냥 그 정의에 의해서 그런 거죠. This is just definition. So in here we will use these two more statements to estimate eigenvalues. Let me show you an example. So find the eigenvalues of matrix A. 2, 3, 3, negative 6. 2, 3, 3, negative 6. The question is, which lambda make this equation satisfy? Which lambda? This is problem. 그렇죠? So first of all, we must find the whole scalar lambda such that the equation a minus lambda I times x is equal to 0, right? Because this is the definition, right? So we have to find out lambda, make this equation has non-trivial solution. Non-trivial solution x. Non-trivial solution x. By the inverter matrix theorem. Inverter matrix theorem is equivalent to finding whole lambda such that matrix A minus lambda I is not invertible, right? In other words, if this matrix invertible, there is a trivial solution, right? But we have to find out lambda such that matrix A minus lambda I is not invertible, right? So how can I find this one? From this one, we can just use the determinant. So determinant of this one should be 0 to make such that matrix to make the matrix equation A minus lambda I times x is equal to 0 as non-trivial solution. Then the question is, because A is like this, A minus lambda I is going to be looks like this. Why? 2, 3, 3, 0, 6 minus 2, 2, 0, 0. So it's going to be this one. So determinant, this one should be 0. Right. First of all, we already talked about determinant of a 2 by 2 case, right? So what was the determinant of 2 by 2? Let's say A, B, C, D. 자, what is that? Determinant of 2 by 2. Who knows? 자, 2 by 매트릭스의 determinant 어떻게 구했죠, 우리? We discussed this one in section, chapter 2.2, 그렇죠? 우진, right? AD minus BC. 그렇죠? Then you can just compute this one, 2 minus lambda times negative 6 minus lambda minus 3 by 3. Then this one is going to be lambda square 얼마예요? 4 lambda negative 12 9, right? Equals 0. By the factorization rule, you can factorize this one as a this one. We will skip this one here, so you can just factorize the second of the polynomial by using your middle school knowledge, 그렇죠? 중학교 때 배웠던 그냥 인수분해 하면 돼요. 그래서 얘가 Eigenvectors of matrix A야, lambda is equal to 3야, lambda is equal to negative 7이 그렇게 되더라 라는 거예요. 그렇죠? 인수분해는 해서 이걸 풀면 돼요. 이걸 만족하는 람다 값이 되는 거죠. Right? Then Eigenvectors of this matrix A is going to be lambda is equal to 3 and or lambda is equal to negative 7. This is just the eigenvalues. So in this case, scalar equation determinant of A minus lambda I equals to 0 is called characteristication of the matrix A. Characteristication of matrix A. This is the characteristication of matrix A. In other words, scalar lambda eigenvalues, scalar lambda is an eigenvalues of n matrix A if and only lambda satisfy such characteristication defined like determinant of A minus lambda I equals 0. This is the characteristication. So if you find the solution for this scalar equation, you're gonna have eigenvalues for the matrix A. That's the characteristication. 자, let me summarize this one 고려하게. 자, 무슨 말인지 이해했죠? 그래서 이제 우리가 저번 시간에 우리가 5.1에서는 이제는 아이겐밸류가 있었을 때 아이겐벡터를 찾는 거는 그냥 뭐예요? 그 호모지니어스 시스템의 솔루션을 찾는 거였죠. 그냥 뭐예요? 그냥 이거의 솔루션을 찾으면 되는 거죠. 그렇죠? 이건 우리가 벌써 다 배웠던 거고. 근데 이제는 이 람다, 이 스칼라 람다를 어떻게 찾을까에 관한 얘기가 지금 하고 있는 거고요. 결국에 쭉쭉쭉쭉쭉쭉 해보다 보니까 요거 determinant of a minus lambda I equals 0의 그리고 이건 그냥 폴리노미얼 방정식이 나오겠죠. 그러니까 람다가 어떤 뭐 폴리노미얼로 나오는 이런 뭐 이 폴리노미얼 그렇죠? 폴리 나오는 요 이퀘이션을 해를 찾는 문제로 바뀌어 버린다. 라고 하는 게 바로 이때 이 이퀘이션이 캐릭터리스티케이션이다 라고 하는 거죠. 그렇죠? Any questions so far? 자, 여기까지 질문. No? Okay. So, in 2x2 case, you can easily solve this one like this. Then, what about this? Larger matrix case. Let's say 4x4. Find the characteristication of this matrix. Then, by solving such characteristication, you're gonna achieve eigenvalues. 자, characteristication. So, for a minus lambda I, right? A minus lambda I. And this is a minus lambda I, 그렇죠? Just a minus lambda I고, determinant of a minus lambda I. It's going to be determinant of this matrix. This matrix. We did not discuss how to solve this determinant in case of n is equal to n is greater than 2, 2, right? We did not discuss how to derive this one, but let's just assume that we can do that. It's going to be 5 minus lambda times 3 minus lambda, 5 minus lambda times 1 minus lambda. We just assume we can do that. 그렇죠? Then, in this case, this one equals 0 is characteristication. In other words, 5 minus lambda to the 2, 3 minus lambda, 1 minus lambda equals 0. This is our characteristication. Or we can rewrite this one as like this. This is our characteristication. And then, which value make this statement true? This equation true? Which value? Lambda is equal to 1. In this case, lambda is equal to. So, which lambda values make this equation true? 자, right. 성우 학생 좋아요. Lambda is equal to 5 or lambda is equal to 3 or lambda is equal to 1. So, in this case, this is called eigenvalues. Eigenvalues of this matrix. Right? It's very, very easy. Right? Even though the concept or theorem or the definition of the eigenvalue and eigenvectors are pretty complicated, but solving technique is very, very simple. Right? Except one thing. We did not discuss the determinant yet. So let's just assume that we can do that. 그렇죠? 이걸 할 수 있다 그냥 가정한 거. 자, 우리 이번 학기 디터미넌트 뺄 거예요. 그래서 우리 얘기 안 했고 그냥 우리 넘어갈 거였는데 디터미넌트 할 수 있다 그냥 가정할 거고 우리가 만약 시험이 나오더라도 다 줄 거예요. 그리고 디터미넌트는 사실 계산하는 게 너무 복잡하기 때문에 사실 여러분들이 디터미넌트를 손으로 계산할 일은 없어요. 사실 2/2를 넘어가는 순간 거의 계산기는 다른 것 프로그램으로 계산을 하지. 그래서 우리도 할 수 있다 그냥 가정하는 것 뿐이에요. 알겠죠? 펼쳐. No? Okay. So this is the characteristication. So expanding the product, we can also write this one. 그렇죠? This is the also characteristication, right? In other words, if A is n by n matrix, then determinant of A minus lambda I is a polynomial of the degree n. So called characteristic polynomial of the matrix A. Characteristic polynomial of matrix A. In this case, because A was a 4 by 4 matrix, the characteristic was polynomial of degree 4. 그렇죠? 4. In this case, this polynomial is called characteristic polynomial. Polynomial. Characteristic polynomial. Primary concept is the eigenvalue 5. Eigenvalue 5 is said to be multiplicity 2 because lambda minus 5 occurs 2 times as a factor of the characteristic polynomial. So because the lambda minus 5 was the factor 2 and 2 times occurs, 그쵸? From here, and here, we just say that eigenvalue 5 have eigenvalue 5 is said to have multiplicity 2. In general, multiplicity of the eigenvalues is a multiplicity of each multiplicity as a root of the characteristication. In this case, like 2. So question is, what the multiplication of the eigenvalue 3 is what? In this case, or multiplicity of the eigenvalue 5 was 2. 그렇죠? Due to the distance. Right? In this case, multiplicity of the eigenvalue 3 is what? Just 1. 그렇죠? Because there is 1. One was skipped it, right? There was 1. So multiplicity of the eigenvalue 1 or 3 is just 1. 그렇죠? This is just our definition. 자, question so far. Please do not focus on the unimportant part. Please focus on the main idea or high level understanding. So this is a characterization which is used to find out eigenvalue. Then you're gonna find out eigenvectors corresponding to each eigenvectors, 그렇죠? Each eigenvalues. This is a characterization. One more concept in chapter 5.2 is similarity. What is similarity? Matrix A and P are n by n matrices. Then A is similar to B if there is invertible matrix P such that P inverse times A times P equals B, or equivalently A is equal to P inverse, because P is invertible, right? In this case, we say A is similar to B. A is similar to B. Writing Q for the P inverse. Writing Q for P inverse, then we have Q inverse P Q A, because by just substitute this one. So in this case, P is also similar to A due to the fact that here. Here. Then we say simply matrix A and P are similar. Matrix A and P are similar to each other. similar each other. If there is the matrix P or Q, like this. In other words, changing A, matrix A, into the similar matrix P inverse A P is called similarity transformation. This is very, very important concept which will be used in the diagonalization, our another factorization. So anyway, so if we change matrix A to the P inverse A P, let's just say P, which is called similarity transformation. Here is theorem 4 in chapter 6.2. If n by matrix A and P are similar, then they have a same characteristic polynomial, hence the same eigenvalue with same multiplicity, because they have same characteristic polynomial. Again, if n by matrix A and P are similar each other, they have, even though two matrices are different, they have same characteristic polynomial. It means that they will have same eigenvalues. It means that they will have same eigenvectors. So, that's the theorem 4. Let's just prove. If A and P are similar, B is going to be the P inverse times A times P. 그렇죠? Then we can compute B minus lambda I. Then we can easily compute again P inverse A P minus lambda P inverse P. Then which is going to be P inverse times A P minus lambda P. It's just because this is just identity. 그렇죠? Then P inverse times A minus lambda I times P. Okay, so to compute the polynomial, characteristic polynomial, we are going to compute the determinant of the P minus lambda I, right? P minus lambda I, and it's going to be the determinant of this one, 그렇죠? P inverse times A minus lambda I times P. Then by the properties of the determinant, we did not discuss this one, but we will just use the property of the determinant here. 그렇죠? 우리 이거 그냥 쓴다고 했어요. 우리 증명하지 않을 거지만 이걸 쓰면은 it's going to be decomposed like this. 그렇죠? And again, determinant P minus 1 times determinant P is going to determine the P inverse times P, because P is invertible. P inverse times P is going to be the identity, so it's going to 1. So determinant of the P minus lambda I is equal to determinant of A minus lambda I, right? In other words, these two matrices, if two matrices are similar, it has the same characteristic polynomial, so it has the same eigenvalues and eigenvectors. That's the theorem 4. Okay. We'll use this theorem in chapter 5.3, diagonalization. But here, let's just remember theorem and definition. Okay. There are a few warning. Matrix 2012, 1002 are not similar, even though they have the same eigenvalues. So please remember that even though they are not have same eigenvalues, the matrix are not similar in some cases, right? And similarity is not same as the row equivalent. If matrix A is row equivalent to P, we already know P is the E times A, where some inverter matrix E, but row operational matrix usually change the eigenvalues. So row equivalent does not mean row matrix A and P are equivalent. So similar. So okay. Question: 자, 한국말로 더 설명 한번 할게요. 자, 아마 이제 여러분들이 마지막 2주 정도 남겨놓고 있는데 좀 정신이 없죠? 조금 어려운 내용들을 계속 나오고 있는데 말했지만 정말 쉬워요. 푸는 건 정말 쉽고 아마 이제 아이겐밸류에서 많은 사람들이 흔히 말해 포기를 하죠. 그렇죠? 절대 그럴 필요 없어요. 절대 그럴 필요 없고 큰 개념만 이해하면 돼요. 그리고 푸는 거는 정말 쉬워요. 이해만 하면. 알겠죠? 자, 챕터 5.2에서 뭐 하고 있었냐면 결국 Characteristication이라는 걸 만들고 싶은 거예요. Matrix A의 Characteristication을 만들어내면 이 Determinant가 0인 Characteristication을 만들죠 싶은 거죠. 그렇죠? 그래서 이걸 만족하는 게 Eigenvalue이기 때문이에요. 그렇죠? 그래서 이걸 어떻게 쭉쭉 해볼 거냐 봤더니 뭐 이렇게 사바이사 할 때는 2발보다 큰 경우 사실 우리가 아직 안 배웠기 때문에 사실 2발밖에 안 배울 거기 때문에 그냥 이렇게 디컴포즈 된다는 걸 그냥 가정할 건데 그때 만들어진 폴리노미얼이 결국에 캐릭터리스 폴리노미얼을 하는 거였고 이거의 해가 결국에 아이겐밸류다 라고 하는 거였고요. 뭐까지 데피니션들이 있었고요. 마지막 시밀러리티라고 하는 컨셉, 유사도라고 하는 컨셉을 배웠고 이 유사도랑 뭐냐, 어떤 매트리스 A와 B가 유사하다면 매트리스 A와 B가 동일한 캐릭터리스티케이션을 가져야 된다. 무슨 얘기냐? 매트리스 A와 B가 아이겐밸류와 아이겐벡터가 같다면 미안해요. 아이겐벡터 같지 않아요. sorry. Sorry about that. Okay. If two matrices have the same eigenvalues, not eigenvectors, only eigenvalues, we just call A and B are similar. 그렇죠? 미안해요. 헷갈렸네. 아이겐밸류와 같다면 매트리스 A와 B는 similar하다라고 하고 그 매트리스 B는 P inverse A, P로 표현된다. arbitrary inverter matrix P. 반대로 B도 A를 이런 텀으로 나타낼 수 있다라고 하는 거였죠. 그렇죠? 그게 시뮬레이터 컨셉이고 이게 이제 바로 우리 마지막 챕터 다이고널라이제이션. 우리가 이제 마지막 배울 또 하나의 팩토라이제이션에서 이런 컨셉들을 쓰도록 하겠습니다. 그렇죠? 자, 질문 여기까지. Question so far. Question. Or comment or whatever. 자, 또 질문해 봐야겠네. 잘 따라오고 있죠? 혹시 궁금하거나 이해 안 되는 부분 있는 친구들? 클리어. 다 이해됐나요? 여러분들? 괜찮아요? 오케이. 서영학수 땡큐. 자, 오케이. So, if we finish chapter 5.3, we will fully understand eigenvalue, eigenvector, right? So please stay tuned before the finishing of this lecture to 12, right? So this is chapter 5.3, diagonalization. Diagonalization. A square matrix A. Square matrix means n by n matrix. 그렇죠? 정사각형이죠. Square matrix A is said to be diagonalizable. Diagonalizable. If matrix A similar to diagonal matrix. Diagonal matrix. That is, if there exists P and T that satisfy A is equal to P, D, P inverse, first some arbitrary matrix P and first some diagonal matrix D. Then we call matrix A is diagonal. Diagonalizable. Diagonalizable. What does it mean? So far we discussed the two factorization technique. LU factorization, right? LU factorization and QR factorization, right? So in here we will talk about one more factorization, diagonalization, which is going to be P, D, P inverse. P, D, P inverse. That's the today's topic. Diagonalization. A is equal to PD P inverse. First of all, let's talk about what's the meaning of these kinds of diagonalization and talk about how to find out this matrix. Okay, this is LU factorization. It was the QR factorization, and this is just called diagonalization. This is the topic of the chapter 5.3. 5.3. To understand this, let me start diagonalization theorem. Diagonalization theorem. On n by n matrix A is diagonalizable. Diagonalizable. In fact, whole scale matrix is not diagonalizable. Matrix A is diagonalizable if and only if matrix A has n linearly independent eigenvalues, eigenvectors. A has n linearly independent eigenvectors. Then matrix A is diagonalizable. Okay. Again, by the way, before that, if matrix A is diagonalizable, or if we can represent this matrix A like this, there are so many kinds of advantages. We will talk about this one later. But if matrix A has n linearly independent eigenvectors, matrix A is invertible. Diagonalizable. This is the diagonalization theorem. Impact. A is equal to P inverse with this diagonal matrix. This diagonal matrix, and if and only if columns of P n linearly independent eigenvectors of matrix A. Eigenvectors of matrix A. In this case, the diagonal matrix of matrix B, eigenvalues of matrix A that correspond respectively to the eigenvectors of in P. In other words, what's the meaning of this one? If matrix A has linearly independent eigenvectors and linear independent eigenvectors, let's say V1, V2, and Vn, which are corresponding to lambda 1, lambda 2, lambda n, then our matrix A can be factorized by P inverse, which is going to be P consists of eigenvectors, linear independent eigenvectors, V1, V2, Vn, and P has the eigenvalues on diagonal, V1, lambda 1, lambda 2, lambda n, and P inverse is going to be P inverse. This is the diagonalization. This kind of factorization is called eigen decomposition. If you are not working in computer science department, so if you are not moved to the other department, during 4 years, you're gonna hear infinitely many times about eigen decomposition. So that means that eigenvalue decomposition, one of the most important issues or on the concept in this semester or in linear algebra part, because there are so many kinds of advantages, this kinds of factorization. 결론 뭐야? 우리 이번 학기에 배웠던 이 아이겐 디컴포지션이라고 하는 결국 이렇게 하면 되는 거예요. 어떤 A가 n개의 리니어리 디펜던트 아이겐 벡터를 가졌을 때는 매트리스 A는 P, D, P 인버스로 이렇게 나눠질 수가 있다라는 컨셉, 아이겐 디컴포지션이라고 하는 컨셉이 이제 이게 바로 팩토라이제이션인데 우리가 배웠던 LU, TQR 다음에 이제 배운 팩토라이제이션인데 아마 여러분들이 컴퓨터 디파트먼트를 떠나지 않고 4년 동안 있고 뭐 대학원도 가고 한다면 아마 여러분들이 정말 무한히 많이 들어볼 단어가 바로 이 아이겐 밸류, 아이겐 팩토라이제, 아이겐 디컴포지션 또는 아이겐 팩토라이제이션 또는 다이고널라이제이션이라고 하는 컨셉이 될 거예요. 그만큼 너무너무 중요한 컨셉이고 너무너무 많은 곳에 쓰일 수 있는 컨셉이기 때문인 거예요. 알겠죠? 조금만 더 집중을 해봐요. 너무너무 중요한 얘기겠죠? In other words, A is diagonalizable if and only if there are enough eigenvectors to form basis of the Rn. basis of Rn. 그 말은 뭐예요? We call such a basis eigenvector basis of the Rn space. Rn space. 그래서 if your eigenvectors are linearly independent, you have n linear independent eigenvector, we will decompose your matrix A, PD, P inverse, where P are the columns of P are n linear independent eigenvectors of the matrix A, and diagonal entries of the T are eigenvalues of matrix A, corresponding to eigenvectors in P. That's the diagonalization theorem. Question. 자, 뭐예요? 우리 아까 시밀러 하는 거 배웠다 했죠? A와 B, 여기서 말하는 D. 다이고널라이제이션 시밀러 하니까 D와 A가 같은 아이겐밸류 가지고 있다는 거 알겠죠? 그래서 이제 이렇게 나눠진다는 걸 뭐 예측을 할 수 있을 거고, 그렇죠? 근데 이제 이게 바로 아이겐밸류 디컴포지션이다 라고 하는 개념이에요. 그렇죠? Question. No? First of all, let's prove. Again, the proof is pretty complicated. So please do not follow hold the line by line. Please just high level understanding. Please just understand in a high level. Okay. Okay. So first of all, observe that if P is any n by n matrix with columns V1, V2, Vn, and if T is any diagonal matrix with diagonal entries lambda 1, lambda 2, lambda n, then A times P, where P is like this, then it's going to be AV1, AV2, AVn. While PD, where P is like this, lambda is this like this. 그렇죠? Then by computing here, because P is like this, this one is going to be lambda 1 V1, lambda 2 V2, lambda n Vn. Now, suppose A is diagonalizable. A should be P inverse. 그렇죠? P inverse. Then write multiplying this relationship by P, then you have AP equals to PD. 그렇죠? 여기죠? AP equals to PD. So each column vector should be same. Let's say this is the equation 1 and equation 2. In this case, A 1 and 2 implies this equation. Equating columns, we find that AV1 is equal to lambda V1, AV2 is equal to lambda V2, AVN is equal to lambda Vn. Sure. Let's say this is equation 3. Since P is invertible, P is invertible, 그렇죠? Each columns V1, V2, Vn must be linearly independent. Linearly independent. Why? By inverter matrix theorem. 그렇죠? 얘가 P가 인버터블하면 얘가 리니어 인버터 해야 된다. 그렇죠? 우리가 P가 뭐예요? 이렇게 리니어 인디펜던트하다 가정했었으니까. Since these columns are non-zero, the equation so that lambda 1, lambda 2, lambda n eigenvalues and lambda 1, v1, v2, vn are corresponding eigenvectors. 그래서 뭐예요? 여기로부터 우리는 v1, v2, vp가 아이겐벡터스고 람다 1, 람다 2, 람다 n이 아이겐밸류스다. 그렇다면 우리가 뭐냐? Binary given any n eigenvectors, use them to construct the columns of matrix P and use the corresponding eigenvalues lambda n, lambda 1, lambda 2, lambda n to construct T by equation 1 and 3. AP is equal to PD. If in fact the eigenvectors are linear independent, then P is invertible. 그렇죠? So AP is equal to PD implies that A is equal to P inverse. P inverse. This is just proof. This is just eigenvalue, eigen decomposition. Eigen decomposition. Okay? This is eigen decomposition. So, if you can find out eigenvectors and eigenvalues, linear independent eigenvectors and eigenvalues, you can decompose your matrix A to the P inverse, then which will be much easier to handle compared to the original matrix A. This diagonalization theorem. Question. 자, 조금 어떠신가요, 여러분? 따라올 만하나요? Question. Question. 인수, thank you. Others? Word question. 괜찮아요? 저 따라올만 하죠? Let me show one more example to help your understanding. So the question was, diagonalize the following matrix if possible. If possible. So your matrix A was 1, negative 3, 3, 3, negative 5, 3, 3, negative 3, 1. So it means that you want to decompose your matrix A as a P inverse, right? If possible, right? In other words, that is, find an inverter matrix P and diagonal matrix D such that looks like this. In other words, the question was finding eigenvectors and eigenvalues of arbitrary matrix A. That's the question. That's the question. That's why you have to know eigenvalue and you have to know how to compute eigenvalues, eigenvectors. Okay? So let's do that. Let's do that. By the way, I will give you 1 minute to understand this question first, and please try to understand by your wording this question. Okay? 자, 여러분 아마 이제 제가 이제 풀어주기 전에 한번 1분을 줄 테니까 여러분들 제가 한번 이걸 읽어보고 도대체 이게 무슨 의미인가, 그리고 이걸 뭘 풀라고 하는 건가를 한번 여러분 한번 고민해보고, 그렇다면 아이겐밸류, 아이겐팩트 찾는 문제라면 이걸 어떻게 찾을 수 있을까 한번 고민을 해봅시다. 1분에 다시 풀어줄게요. Okay, time's up. Okay, so there are 4 steps to implement description in the diagonal theorem. So first of all, you have to find out eigenvalues. 그렇죠? Find the eigenvalues. Then you're gonna find out eigenvectors corresponding to eigenvalues, right? So how to find out eigenvalues? You have to use the characteristication, right? So characteristication. What's that? Determinant a minus lambda I is equal to 0 was characteristication. 그렇죠? Determinant a minus lambda I was equal to 0 was the characteristication, right? So here the characteristication turns out to involve the cubic polynomial that can be factorized because the a was a 3 by 3, right? So if you compute the determinant of this one, it's going to be this one, right? Unfortunately, the mechanics for comparing the eigenvalues, I mean the determinant of the 3 by 3 matrix, more appropriate for the computer when a matrix is larger than 2 by 2. So in most cases, we will just given this polynomial, this characteristication or polynomial, characteristic polynomial. 그렇죠? 계속 얘기했지만 저희 3by 3이 넘어가는 순간 이 디터미넌트를 찾는 건 사실 여러분들이 손을 찾기 너무 어렵기 때문에 기본적으로, 그러니까 특별한 케이스가 아니면 A가 특별한 쉐입이 아니면 너무 어려워서 사실 아마 대부분은 컴퓨터나 계산기로 풀어요. 그래서 우리도 여기서는 그냥 이 디터미넌트는 알고 있다 가정할 거예요. 알겠죠? Anyway, if the a minus lambda I was 1 minus lambda 3, negative 3, negative 5 minus lambda, negative 3, 1 minus lambda, then this one, your characteristic polynomial is going to be like this. And you can factorize to this one like this by rule of the factorization. In Korean, 인수분해. 할 수 있죠? 중학교 때 배운 거로 하면 여기까지만 주면 이건 할 수 있죠? 그렇죠? 마이너스 람다 마이너스 1 times 람다 plus 2 to the 2. 그렇죠? So here eigenvalues. The value satisfying this equation was lambda is equal to 1 and lambda is equal to negative 1. Here we go. 그렇죠? This is the first step, finding eigenvalues. Then in step 2, let's find 3 linearly independent eigenvectors of matrix A. So first of all, we already know lambda is equal to 1 and lambda is equal to negative 2. 그렇죠? Then first of all, let's consider lambda is equal to 1. Then how to find out corresponding eigenvectors? One of the eigenvectors. Because the lambda is equal to 1, ax is equal to 1 times x. 그렇죠? Then we will get a minus lambda in데 because lambda is equal to 1, then a minus identity times x is equal to 0. 그렇죠? Then a minus I is 0, negative 3, negative 6, 3, negative 3, 0 times x is equal to 0. 0 vector, 0, 0. Then if you solve this homogeneous system, you're gonna have 이건 스킵할게요. You're gonna have parameter solution. We will skip this one because we already talked about this one in before the midterm. So solution of this system is going to be more, for example, small x times 1 negative 1, 1. So basis for lambda is equal to 1 is the 1 negative 1, 1. Let's just say that this is one of the eigenvectors corresponding to lambda is equal to 1. Similarly, if lambda is equal to 2, lambda is equal to 2, ax is equal to 2x, which is going to be a minus 2 lambda, 2i times x is equal to 1. Zero. Then this matrix to be 3, 3, 3, there 3, there 3, there 3, 3, 3, 3, x is equal to 0. Let's solve this homogeneous system. But because this is very, very specific case, you can easily low reduce this equation as a 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0 in augmented matrix form, right? So in this case, x1 plus x2 plus x3 is equal to 0, right? So our general solution is going to be 뭐죠? x2 times negative 1, 1, 0 plus x3 times negative 1, 그쵸? negative 1, 0, 1. So there are eigenvectors x like this. So we just consider this one and this one as a basis. So one of the eigenvectors, two of the eigenvectors was the 1, negative 1, 1, 0, negative 1, 0, 1. Then your set of the eigenvectors, v1 and v2, v3, 1, negative 1, 1, negative 1, 1, 0, negative 1, 0, 1. So now we have our eigenvalues and eigenvectors. So you have to check v1 and v2, v3 linear independence set, because it should be linear independence to make a diagonalization. 그렇죠? 이거 아까 그냥 definition이었죠? 그렇죠? Then concept P from the vectors, 그렇죠? Eigenvectors, 그렇죠? In this case, the order of the vectors doesn't matter, 그렇죠? Unimportant. Then we just to define matrix P as a V1, V2, V3 like this. And step 2, construct D from the corresponding eigenvalues. 그렇죠? We already know this one. It is essential the order of the eigenvalues matches the order of the chosen correct columns of P. 그래서 그냥 eigenvalues를 그냥 해당하는 위치에 써주면 돼요. 그래서 P가 we already know eigenvalues 1, negative 2, but interestingly, use eigenvalue lambda is equal to 2 twice, once for each of eigenvectors corresponding to lambda is equal to 2, because for this eigenvectors and this eigenvector and this eigenvector have the same eigenvalues, corresponding eigenvalue as a lambda is equal to negative 2, so it's going to be 1, negative 2, negative 2. Right? So if your matrix is 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1, you can factorize this one, P inverse, where P is equals to 1, negative 1, 1, negative 1, 1, 0, negative 1, 0, 1, and T is equals to 1, 0, 0, 0, negative 2, 0, 0, 0, negative 2. This is the diagonalization, which is also called eigenvalue, eigenfactorization, or the eigendecomposition. 오케이? 일단 한국말 마지막으로 설명할게요. 그래서 뭐냐면 우리가 지금 여기서 뭐 배우고 있느냐? 자, 우리가 이제 LU 팩토라이제이션 배웠고 QL 배웠고 이제 마지막 아니에요. 다음 시간에 하나 더 있긴 한데 이거 익스텐션이긴 해요. 그리고 다이고널라이징 익스텐션인데 계속 헷갈리네. 아이겐디컴포지션 배우고 있는데 뭐냐? A를 PD, P 인버스로 나타내고 싶은 거예요. 근데 P는 아이겐벡터들의 컬럼 벡터들로 이루어져 있는 매트릭스고 D는 그냥 다이고널이 아이겐밸류가 0인 걸로 나타낼 수가 있다라고 하는 게 아이겐 디컴포지션이고, 이거 되면 사실 될 수 있는 쓸 수 있는 게 너무 많아요. 뒤에 설명할게요. 근데 그거 어떻게 할 거냐? 어떻게 해요? 아이겐밸류, 아이겐벡터 찾으면 되니까 아이겐밸류만 찾아서, 아이겐밸류 어떻게 찾을 거냐? 캐릭터리스티케이션 찾아서 캐릭터리스티케이션을 만족하는 람다를 찾아서 아이겐밸류 찾고요. 그 아이겐밸류 주어졌을 때 이렇게 호모지니어스 시스템 만들어서 아이겐벡터를 찾고요. 그렇죠? 그래서 걔네들이 아이겐벡터들이 있는지 네트하면 우리가 P와 D를 그냥 만들어서 쭉 쓰면 끝난다 라고 하는 게 아이겐 디컴포지션입니다. 알겠죠? 자, let me give question. 자, 안녕. 스텝 3에서 벡터 순서 중요하다는 이유는, 순서가 중요하지 않은 이유 뭐냐면 D에 코리스판딩하는 위치에 맞춰주면 되는 거예요. 그러니까 순서가 중요하지 않은 게 아니라 순서를 바꾸면 그러니까 D를 그거에 맞게 바꿔버리면 된다라는 거예요. 알겠죠? 지금 서양스 말하는 게 중요하지 않으니까 순서를 비에 맞게 바꿔도 어쨌든 우리가 원하고 하는 폼이 D는 다이고널이고 P는 아이겐벡터로 구성되어 있는 거는 계속 만족하잖아요. 그렇죠? 그렇기 때문인 거예요. 알겠죠? 자, question. We almost done. So, yeah. Question. No? Okay. So it was the chapter 5.1, 2, 3, right? So next week we'll finish chapter 5, lecture 12, and we will move the last lecture, singular vector decomposition, in chapter 6. Okay? Any other question? No? Right. So please remember that we have one more assignment which cover chapter 6.5 to the chapter 5.3, which is due on June 9, before the lectures. So please remember that. No more question? Right. So that's it. So this is the end of this lecture. And thank you very much. And please remember that we have one more week left before the end of this semester. Okay. Thank you very much and see you next week. 자, 여러분 너무 고생 많으셨고요. 우리 이제 한 주 남았네요. 좀만 더 고생해주고 숙제 7 오늘 나갔어요. 다음 주까지니까 이제 뭐 숙제라 생각하지 말고 여러분 기말고사 공부 따로 한다 생각하지 말고 열심히 풀어보길 바라고 우리 이제 다음 주 화요일날 봅시다. 오늘 고생 많으셨습니다.